Hi guys! Good day! For this session, we'll talk about a more powerful version of the Fourier transform algorithm. Deriving its origins from the computation-intensive discrete Fourier transform algorithm, we'll dive deeper into its computationally optimized version, the Fast Fourier Transform. The Fast Fourier Transform, FFT, is a very efficient method for calculating the discrete Fourier transform, DFT. It's an essential tool in signal processing that allows for the breakdown of a signal into its individual frequency components. The Fast Fourier Transform, FFT, is an advanced algorithm that significantly speeds up the process of calculating the discrete Fourier transform, DFT. The DFT is a mathematical technique used to analyze the frequencies present in a signal or dataset by converting it from the time domain into the frequency domain. The Fast Fourier Transform, FFT, is highly efficient as it significantly reduces the computational complexity of the discrete Fourier transform, DFT, making it practical for various real-world applications. It enables frequency domain analysis, uncovering spectral information about signals that may be obscured in the time domain. The FFT is utilized in numerous fields, including audio and music processing for tasks like audio compression, equalization, and noise reduction, image and video processing for image compression, filtering, and edge detection, telecommunications for modulation, demodulation, and channel equalization, radar and sonar systems for target detection and tracking, and medical imaging techniques such as MRI and CT scans. The FFT improves this process by reducing the number of calculations needed, making it much faster, especially for large datasets. As a result, the FFT is widely used in various applications in signal processing, such as audio and image analysis, telecommunications, and even in solving partial differential equations. By decomposing a signal into its constituent frequencies, the FFT allows for better understanding, filtering, and manipulation of the signal. The Fast Fourier Transform takes advantage of the symmetry and periodicity properties of the discrete Fourier transform by breaking the computation into smaller, recursive steps. This divide-and-conquer approach significantly reduces the number of complex multiplications and additions required, streamlining the calculation process and enhancing overall efficiency. Key concepts in the Fast Fourier Transform include the discrete Fourier transform, which converts a sequence of n complex numbers, representing a time domain signal, into another sequence of n complex numbers that illustrate the frequency domain spectrum. The DFT process involves multiplying the input sequence by complex exponentials corresponding to various frequencies. Moreover, the butterfly diagram serves as a visual representation of the FFT algorithm, illustrating how the computational process is structured into stages that utilize smaller DFTs, helping to clarify the efficient organization of calculations within the algorithm. The discrete Fourier transform is a mathematical technique that transforms a finite series of evenly spaced samples of a function into an equally sized series of complex numbers, which represent the frequency spectrum of that function. The Fast Fourier Transform is an efficient algorithm for computing the discrete Fourier transform, leveraging the DFT's symmetry properties to reduce the computational complexity from O times n squared to O times n log of n. The key idea behind the FFT is its ability to break the DFT computation into smaller, recursively calculated DFTs. This divide-and-conquer approach reduces the number of complex multiplications and additions required for the calculations, thereby enhancing overall signal processing efficiency. The Fast Fourier Transform takes advantage of the inherent symmetry and periodicity characteristics of the discrete Fourier transform. By leveraging these mathematical properties, the FFT breaks down the computation into smaller, more manageable steps that can be solved recursively. This divide-and-conquer strategy allows the algorithm to systematically tackle the problem by reducing it to several simpler subproblems, each of which requires fewer calculations. As a result, the FFT drastically reduces the number of complex multiplications and additions required to obtain the final result. While directly calculating the DFT might involve a prohibitive amount of computational effort, the FFT reduces this complexity significantly, often turning a process that would take O, n squared, time into one that operates in O times n log of n time. This remarkable efficiency not only speeds up signal analysis but also enables the application of Fourier analysis to large datasets across various practical applications. The butterfly diagram is a crucial visual representation used to illustrate the structure and flow of computations within the Fast Fourier Transform algorithm. It visually maps out how the input data is split and combined at different stages of the FFT process. Each butterfly in the diagram represents a specific operation involving pairs of data points being combined and transformed. In the context of the FFT, the butterfly diagram helps to show how smaller discrete Fourier transforms are computed and merged to produce the final output, making it evident how the algorithm efficiently reduces the complexity of the calculations. By organizing the computations into a series of these butterfly operations, the FFT manages to significantly cut down the amount of work required compared to straightforward DFT calculations, thereby speeding up the process of frequency analysis in signals. This diagram not only aids in understanding the algorithm but also serves as a guide for implementing the FFT in programming. Now, let's move on to the radix 2 FFT. The radix 2 FFT is a specific implementation of the Fast Fourier Transform algorithm that enhances computational efficiency by dividing the input signal into two halves at each stage of the process, making it particularly effective for input sizes that are powers of 2. In the Fast Fourier Transform process, the decomposition stage involves dividing the input sequence of n points into two sequences of n over 2 points, comprising even-indexed and odd-indexed samples. Following this, a recursive calculation is performed to compute the discrete Fourier transform of each half sequence. Finally, the DFT of the original sequence is derived by combining the DFTs of these two half sequences through a method known as butterfly computation, which efficiently merges the results to produce the final frequency spectrum. The core operation of the radix 2 FFT is the butterfly computation, which involves two main steps. The use of a twiddle factor, where one of the half-sequence DFT coefficients is multiplied by a complex exponential known as the twiddle factor, followed by the addition and subtraction of the resulting complex numbers to derive the DFT coefficients of the original sequence. The radix 2 FFT is highly efficient, reducing computational complexity, and its relative simplicity in implementation contributes to its popularity across various applications. Moreover, it offers flexibility in accommodating input sizes that are not powers of 2 through techniques such as zero padding or mixed radix algorithms. The radix 2 FFT has limitations, particularly in that it is most efficient for input sizes that are powers of 2, and its memory access patterns can be non-contiguous, which may negatively affect performance on certain hardware architectures. The radix 2 FFT is widely used across various fields, including digital signal processing for tasks such as spectrum analysis, filter design, and audio and video processing, in telecommunications for modulation and demodulation, as well as channel equalization, in radar and sonar for signal detection and processing, and in medical imaging for image reconstruction and analysis. By understanding the principles of the radix 2 FFT and its efficient implementation, one can harness its power to address a wide range of signal processing problems. Learning so far? Now, let's move on to one of the FFT implementations. The decimation in time, DIT. Decimation in time FFT is a specific implementation of the Fast Fourier Transform algorithm that operates by dividing the input sequence into smaller subsequences at each stage of computation, utilizing the principle of decimating the input sequence in time. It works by first decomposing the input sequence of n points into two subsequences, consisting of even-indexed and odd-indexed samples. The DFT of each subsequence is then calculated recursively, and finally, the DFT of the original sequence is obtained by combining the DFTs of the two subsequences through a process known as butterfly computation, which includes multiplying by twiddle factors. The butterfly computation involves two key steps. First, a twiddle factor is introduced by multiplying one of the half-sequence DFT coefficients by a complex exponential known as the twiddle factor. Second, the process involves adding and subtracting the two resulting complex numbers to derive the DFT coefficients of the original sequence. The DIT FFT is highly efficient, achieving a reduction in computational complexity, and its relative simplicity in implementation contributes to its popularity across various applications. Additionally, it offers flexibility by accommodating input sizes that are not powers of 2 through techniques such as zero padding or mixed radix algorithms. There's another FFT implementation named as decimation in frequency FFT. This is another efficient implementation of the Fast Fourier Transform algorithm that, unlike decimation in time FFT, which divides the input sequence in time, focuses on dividing the output sequence in frequency. The DIF-FFT operates through a process of decomposition, where the output sequence of n points is divided into two subsequences, the first n over 2 points and the last n over 2 points. The DFT of the original sequence is then obtained by combining the DFTs of these two subsequences using a process known as butterfly computation, along with multiplication by twiddle factors, while the DFTs of the subsequences themselves are calculated recursively. The butterfly computation and twiddle factors in this context bear a resemblance to those used in the decimation in time Fast Fourier Transform algorithm. Both involve the process of combining inputs in a way that efficiently computes the discrete Fourier transform. However, it's important to note that the order in which the operations are executed differs slightly. In the DIT-FFT, data is processed in a specific sequence that emphasizes the time domain, which affects how the input data is rearranged and combined. This difference in operational order can lead to variations in how the intermediate results are generated and ultimately influence the overall performance and efficiency of the computation. Understanding these nuances is crucial for optimizing FFT algorithms for specific applications and ensuring accurate results. The decimation in frequency Fast Fourier Transform offers several significant advantages, primarily its efficiency, simplicity, and flexibility. It reduces the computational complexity, making it highly efficient for processing data. Additionally, the algorithm is relatively straightforward to implement, which contributes to its accessibility for developers. Moreover, DIF-FFT is flexible, allowing for adaptation to handle input sizes that are not strictly powers of 2, thereby broadening its applicability in various computational scenarios. Linear filtering is a fundamental signal processing technique that modifies the frequency components of a signal, traditionally achieved in the time domain through convolution. However, the Fast Fourier Transform provides a more efficient alternative by allowing the filtering operation to be performed in the frequency domain. This approach leverages the advantages of FFT to enhance processing speed and efficiency, making it a valuable method in modern signal processing applications. The process of filtering an input signal using a filter impulse response (FIR) filter in the frequency domain involves several key steps. First, the input signal and the filter impulse response are converted to the frequency domain using the Fast Fourier Transform. Next, the frequency domain representation of the input signal is multiplied by the frequency domain representation of the filter impulse response. This multiplication effectively applies the filter to the input signal in the frequency domain. Finally, the product obtained from this multiplication is converted back to the time domain using the inverse Fast Fourier Transform, resulting in the filtered output signal. Frequency domain filtering offers significant advantages in terms of efficiency and flexibility, particularly for large input signals and filter lengths. When utilizing the Fast Fourier Transform algorithm, frequency domain filtering can be substantially more efficient than traditional time domain convolution. Additionally, this approach enables the implementation of complex filtering operations, such as frequency selective filtering, noise reduction, and equalization, efficiently, thereby enhancing the overall versatility and effectiveness of signal processing techniques. Frequency domain filtering offers significant advantages in terms of efficiency and flexibility, particularly for large input signals and filter lengths. When utilizing the Fast Fourier Transform algorithm, frequency domain filtering can be substantially more efficient than traditional time domain convolution. Moreover, this approach enables the implementation of complex filtering operations, such as frequency selective filtering, noise reduction, and equalization, efficiently, thereby enhancing the overall versatility and effectiveness of signal processing techniques. To make the FFT algorithm concrete, let's work through a quick numerical example. We'll take a simple 4-point sequence, 1, 2, 3, 4, and walk through the decimation in time procedure. The first step in the DIT algorithm is the decimation itself. Since we have 4 points, we split them by their index parity. We take the even indexed samples, indices 0 and 2. That gives us 1, 3. We take the odd indexed samples, indices 1 and 3. That gives us 2, 4. We've now broken our 4-point problem into 2 2-point problems. Next, we compute the FFT of these two halves. Since these are length 2 sequences, the math is trivial. For the even half 1, 3, the 2-point transform is simply 1 plus 3, 1 minus 3, giving us 4, negative 2. For the odd half 2, 4, we get 2 plus 4, 2 minus 4, giving us 6, negative 2. These are the frequency components of the subsequences. Now we combine these two halves to get the final 4-point DFT. We can't just concatenate them. We need to apply the twiddle factors, which account for the phase shift between the even and odd samples. 4n equals 4. The twiddle factors are the fourth roots of unity. Let's recall them. W0 is 1. W1 is negative j. W2 is negative 1. And W3 is j. We combine them using the standard butterfly equations. Notice we take x sub even of 0 and x sub odd of 0 for the first and third outputs, and x sub even of 1 and x sub odd of 1 for the second and fourth. Let's compute them one by one. X of 0 is equal to 4 plus 1 times 6 equals 10. This is the DC component. X of 1 equals negative 2 plus negative j times negative 2 equals negative 2 plus 2j. X of 2 is equal to 4 plus negative 1 times 6 equals negative 2. This is the Nyquist component. X of 3 equals negative 2 plus j times negative 2 equals negative 2 minus 2j. And there we have our final spectrum. The DFT of 1, 2, 3, 4 is 10, negative 2 plus 2j, negative 2, negative 2 minus 2j. If we do a quick sanity check, we can compare x of 0 to the sum of the original sequence. 1 plus 2 plus 3 plus 4 equals 10, which perfectly matches our x of 0 result. That confirms our computation is correct. Note that x of 1 and x of 3 are complex conjugates of each other, which is expected for a real-valued input signal. The DIT algorithm just saved us a few multiplications compared to the full DFT matrix. Okay, any question? Let's now move to decimation in frequency. For this DIF example, we process the same input, 1, 2, 3, 4, but we leave it in natural order. Stage 1, we pair samples spaced by 2 positions, half of n. Add the pairs. 1 plus 3 is equal to 4, and 2 plus 4 is equal to 6. These form the even frequency components. Subtract them. 1 minus 3 equals negative 2, and 2 minus 4 equals negative 2. These form the odd frequency components. Stage 2. Now we apply the twiddle factors. 4n equals 4. We use W04 equals 1, and W14 equals negative j. The even outputs, x of 0, x of 2, combine the sums directly. The odd outputs, x of 1, x of 3, combine the differences after multiplying by the twiddle factor negative j. Crunching these butterflies gives the final spectrum. X sad face 10, negative 2 plus 2j, negative 2, negative 2 minus 2j. The result is mathematically identical to the DIT-FFT. The key difference. DIF splits the frequency domain first, keeping the input in natural order, making it highly efficient for hardware implementations. Now it's your turn. Work on these examples using DIT and DIF FFTs. You can pause this video and review to catch up with the previous solutions. If you have questions, just give me a beep. Practice DIF, and you're good to go. You may also try with 8 elements. Happy learning, and see you in our next learning sessions.